Pluto is a distant and mysterious dwarf planet, which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen? And what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets that could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space is about figuring out how three things in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms as libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is as libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the IL movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zeipel, Chi, and Lagrange, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems all over the place, this oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem wild and random, some patterns, and rules keep everything in order. All of these components help keep Pluto's orbit stable, making sure it doesn't crash into Neptune or get thrown off course. This three-body problem helps in understanding how these parts change because of the way these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, distant worlds, and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn helps a bit too. These tests show that Jupiter's gravity alone is strong enough to make sure Pluto stays on a stable path for a really long time, even billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is really important. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been super helpful for scientists to figure out how Pluto moves in space. These simulations use tricky math to mimic how Pluto and other space objects like Neptune pull on each other. By changing little details in the simulations, astronomers can see how even small tweaks can make a big difference in where Pluto goes. Back in the late 1980s, these simulations showed something really interesting about Pluto's path. Even though it has things like azimuth and latitude libration to keep it steady, its orbit can still be pretty wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking really different. But even with all this chaos, Pluto's orbit stays stable for a super long time, like billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when it involves chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or oversimplification can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us how our knowledge about the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune despite all these complex forces trying to keep such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a pivotal figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification as not a demotion, but a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The intrigue of these unknowns, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the cosmos. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to bridge complex scientific concepts with futuristic visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's insights on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as a crucial area of study, not just for academic curiosity, but for practical implications. The potential collision between Pluto and Neptune, for instance, is not just a theoretical scenario, but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist outlook pushes us to consider the broader implications of such events, from the impact on our understanding of the solar system to the potential need for future space interventions. Kaku's perspective underscores the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's views converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but anticipating how they might change in the future. The potential collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for robust scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational influences acting on them. Therefore, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behaviors and any potential risks they might pose. While the scenario of a Pluto-Neptune collision is largely speculative and considered improbable with our current understanding, it underscores the importance of continuous research and observation in astronomy. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring that we stay informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous exploration and a flexible understanding of our universe. The potential collision scenario, while highlighting the dynamic and complex interactions within our solar system, ultimately reminds us of the vast, still uncharted territories in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving cosmos.